Good day, students. Today I will be discussing with you another topic in fluid mechanics. But before that, let us have a quick review of our previous discussion. If you can recall, we discussed the different conservation laws and the corresponding equation. We have the continuity equation for the conservation of mass, the Bernoulli equation for the conservation of momentum, the general energy equation for the conservation of energy. We also discussed the mechanical energy and efficiency, among others. Today, we will be dealing with steady incompressible flow in pressure conduits. Fluid flow in circular and non-circular pipes is commonly encountered in practice. The hot and cold water that we use in our homes is pumped through pipes, as you can see here in this presentation. Water in a city is distributed by extensive piping networks. Oil and natural gas are transported hundreds of miles by large pipelines. Blood is carried throughout our bodies by arteries and veins. The cooling water in an engine is transported by hoses to the pipes in the radiator where it is cold as it flows. Finally, the thermal energy in a hydronic space heating is transferred to the circulating water in the boiler, and then it is transported to the desired location using pipes. Fluid flow is classified as either external and internal, depending on whether the fluid flow is forced to flow over a surface or in a conduit. Internal and external flow exhibit very different characteristics. In this chapter, we will consider internal flow where the conduit is completely filled with the flow and the flow is driven primarily by a pressure difference. This should not be confused with an open channel flow where the conduit is partially filled by the fluid and thus the flow is partially bounded by solid surfaces, as in an irrigation ditch, and flow is driven by gravity alone. The term pipes, duct, and conduit are usually used interchangeably for flow sections. In general, flow sections of circular cross-sections are referred to as pipes, especially when the fluid is a liquid, and flow of non-circular cross-section as ducts, especially when the fluid is a gas. Small diameter pipes are usually referred to as tubes. Given this uncertainty, we will use more descriptive phrases such as a circular pipe or a rectangular duct whenever necessary to avoid any misunderstanding. You have probably noticed that most fluids, especially liquids, are transported in circular pipes. This is because pipes with a circular cross-section can withstand large pressure differences between the inside and the outside without undergoing significant distortion. Non-circular pipes are usually used in applications such as the heating and cooling systems of buildings, where the pressure difference is relatively small. The manufacturing and installation costs are lower and the available space is limited for ductwork. The fluid velocity in a pipe changes from zero at the surface because of the no-slip condition to a maximum at the pipe center. In fluid flow, it is convenient to work with an average velocity, denoted by V average in this presentation, which remains constant in incompressible flow when the cross-sectional area of the pipe is constant. The average velocity in heating and cooling applications may change somewhat because of the changes in density with temperature. But in practice, we evaluate the fluid properties at some average temperature and treat them as constants. The convenience of working with constant properties usually more than justifies the slight loss in the accuracy. The value of our average velocity at some streamwise cross-section is determined from the requirement that the conservation of mass principle be justified. That is, the mass flow rate is equal to density multiplied by the average velocity multiplied by the cross-sectional area. It can also be expressed in terms of the integral equation, as you can see here in this presentation. By the end of this topic, you should be able to have a deeper understanding of laminar and turbulent flow in pipes and the analysis of fully developed flow. Calculate the major and minor losses associated with pipe flow in piping networks and determine the pumping power requirements. This will be the outline of my presentation. So let's start with laminar and turbulent flow. The difference between laminar and turbulent flow is depicted here in this illustration. On the left side, you can see a laminar flow, while on the right side, we have the turbulent flow. Laminar flow is characterized by smooth streamlines and highly ordered motion. On the other hand, turbulent flow characterized by velocity fluctuations and highly disordered motion. The transition from laminar flow to turbulent flow in a flow is not happening suddenly. Most flows encountered in practice are turbulent. Laminar flow can be encountered when highly viscous fluids such as oil flows in small pipes or narrow passages. The transition from laminar to turbulent flow depends on the geometry, surface roughness, flow velocity, surface temperature, and the type of fluid. Osborne Reynolds discovered that the flow regime depends mainly on the ratio of inertial forces to the viscous forces in the fluid. This ratio is now known as the Reynolds number. The Reynolds number can be computed for internal flow in a circular pipe in terms of the average velocity, the diameter, and then the kinematic viscosity. For non-circular pipes, the diameter can be written in terms of the hydraulic diameter. Say for example, we have a square cross-section. We can write the hydraulic diameter in terms of 4 times the cross-sectional area over the wetted perimeter. The Reynolds number at which the flow becomes turbulent is called the critical Reynolds number. The value of the critical Reynolds number is different for different geometries and flow conditions. For internal flow in a circular pipe, for example, the generally accepted value of the critical Reynolds number is 2300. The hydraulic diameter is defined such that it reduces to ordinary diameter for circular tubes. You can see here depicted the hydraulic diameter if we have a square duct, if we have a rectangular duct, and we have a circular tube. It certainly is desirable to have a precise values of Reynolds numbers for laminar, transitional, and turbulent flows. But this is not the case in practice. It turns out that the transition from laminar to turbulent flow also depends on the degree of disturbance of the flow by surface roughness, pipe vibrations, and fluctuations in the flow. Under most practical conditions, the flow in a circular pipe is laminar for Reynolds number less than or equal to 2300, turbulent for Reynolds number greater than or equal to 4000, and transitional in between those values. Let us have an example for us to better understand the laminar and turbulent flow and the use of the Reynolds number in order to identify the type of flow. We have here an oil with a specific gravity of 0.85 and a kinematic viscosity of 1.8 times 10 to negative 5 meters squared per second. In a refinery flows through a 10 centimeter diameter pipe at 0.5 liter per second. We are to determine whether the flow is turbulent or laminar. Here we are given with a specific gravity, the kinematic viscosity, the diameter, and also the flow rate. We can also convert the flow rate to meter cube per second for uniformity of dimensions. The unknown is the Reynolds number because it will help us identify if it is laminar or turbulent. The Reynolds number is defined as the ratio of the average velocity multiplied by the diameter to the kinematic viscosity. The average velocity, on the other hand, can be computed using our relationship in terms of the volume flow rate and the cross-sectional area. Thus, we can substitute this value in the Reynolds number equation and obtain the Reynolds number to become, as you can see here in this presentation. So, substituting the value from the given, we can get the Reynolds number to be 353.6777, which is non-dimensional. So the flow is laminar since the Reynolds number is less than the critical Reynolds number, which is 2300. So this is how we can ascertain if the flow is laminar or turbulent. Now that we understand the difference between laminar and turbulent flow, we are now ready to discover the entrance region. Consider a fluid entering a pipe at a uniform velocity as shown here. So we have this uniform velocity of the fluid entering the pipe. Because of the no-slip condition, the fluid particle in the layer in contact with the surface of the pipe come to a complete stop. This layer also causes the fluid particles in the adjacent layers to stop or slow down gradually as a result of friction. To make up for this velocity reduction, the velocity of the fluid at the midsection of the pipe has to increase to keep the mass flow rate through the pipe constant. As a result, a velocity gradient develops along the pipe. The region of the flow in which the effects of the viscous shearing forces caused by the fluid viscosity are felt is called the velocity boundary layer, or just the boundary layer. So here we can see the velocity boundary layer. The hypothetical boundary surface divides a flow in a pipe into two regions. The boundary layer region, in which the viscous effects and the velocity changes are significant, and the irrotational flow region, in which the frictional effects are negligible and the velocity remains essentially constant in the radial direction. So this part here is the irrotational core flow region, and this part here is the velocity boundary layer region. The thickness of this boundary layer increases in the flow direction until the boundary layer reaches the pipe center and thus fills the entire pipe as shown here in this figure. The region from the pipe inlet to the point at which the boundary layer merges at the center line is called the hydrodynamic entrance region. So from this point here at the entrance to the point where our velocity boundary layer merges at the pipe center is the hydrodynamic entrance region. And the length of this region is called the hydrodynamic entry length. Flow in the entrance region is called hydrodynamically developing flow, since this is the region where the velocity profile still develops. The region beyond the entrance region, in which the velocity profile is fully developed and remains unchanged, is called the hydrodynamically fully developed region. So this region here now, where our velocity profile is fully developed, is our fully developed region. The flow is said to be fully developed when the normalized temperature profile remains unchanged as well. Hydrodynamically developed flow is equivalent to fully developed flow when the fluid in the pipe is not heated or cooled, since the fluid temperature in this case remains unchanged. You can see here another depiction of the development of the velocity boundary layer in the pipe. You can see that the hydrodynamically developing flow is called the unestablished flow in other literatures, and our fully developed region is called the established flow, wherein the flow is already established and there's no changes in the velocity profile expected in this point. The velocity profile in the fully developed region is parabolic, as you can see here, in laminar flow, and somewhat flatter or fuller in turbulent flow due to eddy motion and more vigorous mixing in the radial direction. The time average velocity profile remains unchanged when the flow is already fully developed. You can see here in this figure the variation of the wall's shear stress in the flow direction for a flow pipe from the entrance region into the fully developed region. We have here another term we call the hydrodynamic entry length, which we already discussed, is usually taken to be the distance from the pipe's entrance to where the wall shear stress reaches within about 2% of the fully developed value. So you can see here our velocity boundary layer as well as the entrance region. Our entrance region, or the hydrodynamic entry length, is denoted by the symbol LH, as you can see here. Our fully developed region is also shown here. So basically we can divide the flow into two regions. We have the entrance region, wherein the flow is not yet established, and the fully developed region where the flow is already established. For laminar flow, based on Case and Crawford and Shah and Batty, we can compute the hydrodynamic entry length based on the Reynolds number and the diameter of the pipe. This is almost equal to 0.05 multiplied by the Reynolds number and the diameter of the cross-sectional area. For turbulent flow, we also have another equation to get the hydrodynamic entry length, and that is 1.359 multiplied by the diameter and the Reynolds number raised to the power of 1/4. So whenever you wanted to determine the length in the pipe wherein the flow is not yet established, where there is still changes, where there is still irrotational flow of the fluid, then you can use this formula, whether it is laminar or turbulent, in order to get the region in the pipe where the flow is not yet fully established, and the point or the region where the flow is expected to be fully established. Take note that this is very important in the design of piping system. In many pipe flows of practical engineering interest, the entrance effects become insignificant beyond a pipe length of 10 diameters. Thus, for turbulent flow, we can write our hydrodynamic entry length as simply the product of 10 and the diameter of the pipe. So let's have another example for us to better understand this idea of hydrodynamic entry length. We have the same problem as example number 1, it's just that we are now looking for the approximate distance from the pipe entrance to the first point at which the flow is already established. So we are given with the specific gravity, the kinematic viscosity, diameter, and the flow rate. And we are looking for the LH, or the hydrodynamic entry length, for us to know where the point where the flow is already established. From the previous example, the flow is found to be laminar. That's why we can use the formula for the laminar. If the Reynolds number here is 353.6777 based on the example number 1, then using the formula for hydrodynamic entry length for laminar flow, we can get the hydrodynamic entry length as equals to 1.7684 meter. Therefore, the flow will be fully developed or established at a pipe section 1.7684 meters from the entry point. Now that we already know what the entrance region is, we are now ready to dig deeper to laminar flow in pipes. If you can still recall, the flow in the pipe is considered to be laminar for Reynolds number less than or equal to 2,300. And the flow is fully developed if the pipe is sufficiently long relative to the entry length, so that the entrance effects are negligible. In this section, we consider the steady laminar flow of an incompressible fluid with a constant properties in a fully developed region of a straight circular pipe. So you can see here this parabolic velocity profile, which denotes that it's already in the fully developed region. So this equation for the velocity profile is already based on the fully developed region that is beyond the hydrodynamic entry region. So we can write the velocity profile of the fully developed flow in terms of the average velocity and the radius with respect to the center line. So if r is the radius of the pipe, our small r is the any distance from the center line. The maximum velocity based on this equation, if we take r equals to 0, because as you can see, the maximum velocity here happens at the center line. It means that the small r is equals to 0. It's just therefore equals to 2 times of the average velocity, because this portion here will become 0. The maximum velocity again occurs at the center line where r is equals to 0. The average velocity in fully developed laminar flow is therefore 1/2 of the maximum velocity. So if we have the maximum velocity, we can get the average velocity by dividing it by 2. Let us now define another quantity, a quantity of interest in the analysis of pipe flow, which is called the pressure drop, since it is directly related to the power requirements of the fan or pump to maintain the flow. The pressure loss, which is applicable to fully developed internal flows, it can be applied for both laminar or turbulent, circular or non-circular pipes, smooth or rough surfaces, horizontal or inclined pipes. So our delta P, or our pressure loss, can be written in terms of this equation that you can see here in this presentation. Our dynamic pressure is denoted by this term here, this quantity, and then we also have the Darcy friction factor, which is denoted by this F here. It is also called Darcy-Weisbach friction factor. For circular pipe, which is having a laminar flow, our Darcy friction factor or Darcy-Weisbach friction factor can be computed simply using the formula 64 over Re. So therefore, if you have a Reynolds number and the pipe is circular and the flow is laminar, then you can get the Darcy friction factor, and you can already use that in order to compute for the pressure loss. And once you have the pressure loss, then you can multiply that with the volume flow rate in order to get the pumping power requirements. The head loss, which is also applicable to those type of flows discussed for pressure loss, can be written as our pressure loss divided by the product of our rho g, which is our specific weight. So if you have the pressure loss, then you can also get the head loss. And the pumping power, which is used to overcome pressure loss, again can be written as the product of the flow rate and the pressure loss, or it can also be written based on the volume flow rate and the rho GHL in terms of our head loss. So our concern here is to compute for the head loss or the pressure loss so that we can get the pumping power requirements. So you can see here in this illustration that the pumping power requirement for a laminar flow piping system can be reduced by a factor of 16 by doubling the pipe diameter. That means that if the pipe diameter is larger, then the power requirement required for a laminar flow piping system would become lesser. For horizontal pipes experiencing laminar flow, our average velocity in that pipe can be computed using the formula here. The volume flow rate can also be computed. For inclined pipes, on the other hand, which has a laminar flow, we can also compute the average velocity and the volume flow rate. So take note that if this theta is equal to 0, this would reduce to a horizontal pipe. So this therefore is a general equation which we can use even for horizontal pipe. We just substitute theta equals to 0 in that case. The relationships that we have so far is based on circular pipes. How about for non-circular pipes? You can see here in this table the friction factor relations for fully developed laminar flow in pipes of various cross-section, whether it's circle, rectangular, ellipse, or isosceles triangle. The Reynolds number for flow in these pipes is based on the hydraulic diameter, which is equals to 4 times the cross-sectional area divided by the wetted perimeter. So if you wanted to get the friction factor, if you have this kind of configuration, then you will use this formula that you can see here based on the ratio of A and B. The value of A and B is also denoted here in this presentation, also in terms of theta. So if you have these dimensions, then you can get the ratio A and B and check what formula it belongs to. Then when you identify already the formula, then you can substitute the Reynolds number in that formula to get the friction factor. And once you have the friction factor, then you can go back to our general formula for the calculation of our pressure loss and head loss by substituting this Darcy friction factor or Wisbach friction factor in that general formula. So let us have an example for us to illustrate how to get the different quantities in relation to laminar flow. We have the same problem as example 1 and example 2, but this time we are to find the center line velocity, the velocity at a radius of 20 mm, the friction factor, shear stress at the pipe wall, and the head loss per meter of pipe length, and the pipe pumping power requirements to overcome the pressure drop. So we are given with the specific gravity, the kinematic viscosity, the diameter, the volume flow rate, and we are looking for the maximum velocity. The velocity at R is equal to 20 mm, the friction factor, the shear stress at the wall of the pipe, the head loss per meter of pipe length, and the pumping power requirement to overcome the head loss. From the previous example, the Reynolds number is already computed and the flow is already identified to be laminar. So therefore, we can use the equations that we have for laminar flow as discussed in the previous slide. The center line velocity is the maximum velocity if that is for a laminar flow. So therefore, the average velocity was already found to be, in the previous example, to be 0.0366 meter per second, substituting the value of the volume flow rate and the diameter, the equation for the average velocity. So therefore, we can get the maximum velocity or the center line velocity, and that is equals to 0.1273 meter per second. So if you wanted to know the maximum velocity in the pipe of the fluid, then you can get that using the same step if it is a laminar flow. So the center line velocity is again 0.1273 meter per second. The velocity at R is equal to 20 mm can be derived using the equation for the velocity profile if it is a laminar flow, and it is written as based on this equation here in terms of the average velocity and the ratio of the radius with respect to the total radius. So we know that R is 20 mm and that is 0.02 meter. We convert it, and also we know that the radius of this pipe is 5 cm since the diameter is 10 cm. So we just divide it by 2 and substitute also the value of the average velocity that we already computed. Then we can get the velocity at a radius of 20 mm. So as you can see, using this equation, we can definitely get the velocity at the various points of the pipe flow if we already identified it to be a laminar flow. For the friction factor for circular pipe having laminar flow, we can use the formula 64 over RE. So we already know the Reynolds number, so we can get already the friction factor. So that is 0.180. So this is a non-dimensional quantity. For the shear stress at the wall, we can use the formula 8 multiplied by the shear stress of the wall divided by rho and multiplied by the square of the average velocity. So rearranging this formula, we can get the shear stress at the pipe wall. So take note that we can rearrange this formula to get for the shear stress. Since we already know the value of those quantities, we can substitute them and get the shear stress at the pipe wall. So the shear stress at the pipe wall would be 0.0779 Newton per meter squared. So it's important also to know the shear stress at the pipe wall because it would also affect the wall. It would also affect the quality of the material and the kind of selection of material that you will choose for the wall. For the head loss per meter of pipe length, so take note that it's per meter, therefore our length would be 1 meter if this is the case. So it can be computed using this formula and substituting the value that we already know. And again, our length would be 1 meter since this is per meter of pipe length. Then we can get the head loss to be 0.000374 meter. So this head loss is per meter of the pipe length. For the pumping power requirement, we can use the formula that we already have a while ago. We just multiply the volume flow rate and the rho GHL. So substituting those values, we can get the pumping power requirement to be 0.00156 watts. So the power input in the amount of 0.00156 watt is needed to overcome the frictional losses in the flow due to viscosity. So we were able to compute the different unknown quantities for laminar flow. Again, some of this equation is only applicable if you have laminar flow, and the other equation, some of the equations are also applicable if you have turbulent flow. Another example, we have oil at 20 degrees Celsius. The various properties are also given already. The density and the dynamic viscosity is flowing steadily through 5 centimeter diameter, 40 meter long pipe. The pressure at the pipe inlet and outlet are measured to be 745 and 97 kilopascal. Determine the flow rate of oil through the pipe assuming the pipe is horizontal, inclined 15 degrees upward, and inclined 15 degrees downward. We will also verify that the flow through the pipe is laminar. So we already have this given that you can see here, and we are looking for the volume flow rate at those various scenarios stated here. The volume flow rate in all three cases can be computed using our general equation for the volume flow rate for inclined, and whether it is horizontal, we can still apply this formula. So for the volume flow rate of the oil through the pipe, assuming the pipe is horizontal, meaning our theta would be equals to 0, then substituting theta is equals to 0, this portion here will become 0. So it would reduce to this equation here. So substituting the value, we can get the volume flow rate to be 0.00311 meter cube per second. The volume flow rate when the pipe is inclined 15 degrees upward, we can use the same formula, but now our theta would be positive 15 since it is inclined 15 degrees upward. So substituting those values that we already have, we can get the volume flow rate to be 0.00267 meter cube per second. So finally, when the flow is inclined 15 degrees downward, then we can still use the same formula, but this time our theta would be negative 15. So the volume flow rate would be 0.00354 meter cube per second. So if you compare all of the volume flow rate, the maximum volume flow rate would happen if the pipe is inclined 15 degrees downward. So we will use this value to verify that the flow of the pipe would be laminar. So again, we will use the maximum volume flow rate in all of the cases, which is 0.00354 meter cube per second. The rationale for choosing the maximum volume flow rate is because if it is laminar with this volume flow rate, then obviously the other volume flow rate which is lesser than this would be laminar. So the maximum average velocity can be computed using this volume flow rate using the formula that you can see here. So the maximum average velocity is 1.802 meter per second. Then we can get the Reynolds number also since we already have the average velocity, substituting the diameter as well as the kinematic dynamic viscosity as well as the density. So we can get the Reynolds number to be almost 100. So based on this, the Reynolds number is much less than 2,300. Therefore, the flow is laminar for all three cases. So we were able to verify that the flow through the pipe is laminar. Now that we already know how to compute the different quantities in laminar flow in pipes, now we are ready to dig deeper to turbulent flow in pipes. Most flows encountered in engineering practice are turbulent, and thus it is important to understand how turbulence affects wall shear stress. However, turbulent flow is a complex mechanism dominated by fluctuations, and despite tremendous amounts of work done in this area by researchers, the theory of turbulent flow remains largely undeveloped. Therefore, we must rely on experiments and the empirical or semi-empirical correlations developed for various situations. So you can see here in this presentation the comparison of the velocity profile for laminar flow and turbulent flow. Turbulent flow is characterized by random and rapid fluctuations of swirling regions of fluid called eddies throughout the flow. You may also encounter this when you are riding on a plane when the cabin crew would say that we are experiencing turbulence. So that is an example of a turbulent flow. That problem is not yet resolved even nowadays because of the complications on the analysis of turbulent flows. That's why there's no solution yet to the turbulence that we experience when we are riding on the airplane, for example. In analyzing turbulent flow, it is important to use the Darcy friction factor. But since we cannot use directly some formula, it may be helpful for us to use the Moody chart. The Moody chart represents the Darcy friction factor for pipe flow as a function of the Reynolds number and the ratio of epsilon to the diameter over a wide range. It is probably one of the most widely accepted and thus used charts in engineering. Although it is developed for circular pipes, it can also be used for non-circular pipes by replacing the diameter of the pipe with the hydraulic diameter. So this chart here is our Moody chart. So this chart gives us the Darcy friction factor if we have the Reynolds number and intersecting it with the ratio of the epsilon to the diameter. So epsilon there is the roughness of the pipe, and it can be computed. You can get it based on the kind of material that you use for the pipe as shown here. So you just intersect the two value, the Reynolds number. Say for example you have a Reynolds number and then you intersect it with the ratio of the epsilon or the roughness to the diameter, then you can get there the Darcy friction factor. The friction factor, therefore, in fully developed turbulent pipe flow depends on the Reynolds number and the relative roughness. So the ratio epsilon over d is called the relative roughness. Based on the Colebrook equation, we can get the friction factor by substituting the known values and then solving for the f. So sometimes it would be helpful to solve it by using shift solve property of our scientific calculator because both f is present in both sides of the equation. So this equation is again the Colebrook equation, and you can see here that we can get the friction factor based on the ratio of the ratio called the relative roughness, and if we have the Reynolds number. This is only applicable if we have a fully developed turbulent pipe flow. So do not use this equation if you have a laminar flow. Instead, you use the 64 over Re if the flow is laminar. This one is only for turbulent. So this table gives us the equivalent roughness values for new commercial pipes. Say for example, you have glass or plastic. So if you have a glass or plastic, if you can feel it, it's actually a very smooth surface. That's why the roughness would be considered as 0. You can also see here the different roughness for other types of materials. Say for example, you have stainless steel. So the roughness in feet is 0.00007, and then we have 0.002 mm if it is in the metric system. So you can use this table later on if you have, for example, a selection of type of pipe and you wanted to get the roughness for the ratio relative roughness, which is E over D. You can see here in this table also that the friction factor is minimum for a smooth pipe and increases with the roughness. So if the smooth pipe, if we have a smooth pipe, we have the friction factor here equivalent. If we have maximum, say for example here 0.05, then we can also get the friction factor. So it is a function of the friction factor is a function of the relative roughness. In the design and analysis of piping system that involve the use of Moody Chart or the Colebrook equation, so either of the two is applicable. So we can use the Moody Chart or the Colebrook equation to get the Darcy friction factor. We usually encounter three different types of problem. The fluid and the roughness of the pipes are assumed to be specified in all of these cases. The first problem is to determine the pressure drop or head loss when the pipe length and diameter are given for a specified rate or velocity. The second type of problem is determining the flow rate when the pipe length and diameter are given for a specified pressure drop or head loss. And finally, determining the pipe diameter when the pipe length and flow rate are given for a specified pressure drop or head loss. So if that is the case, the head loss, flow rate, and diameter can be computed using this formula that you can see here. So again, be careful when using this formula because this is just applicable to turbulent flow. You can see also here the range of the Reynolds number by which this formula is applicable. So you can see here. So you can also see that some of the formula is applicable for Reynolds number that is in the transitional region. So you can get the head loss, you can get the volume flow rate, and the diameter of the pipe in terms of these quantities that you can see here in this presentation. So let us have an example for us to better understand the turbulent flow. So we have the same similar problem actually. So this time we have water at 60 degrees Fahrenheit. And we are given with the property also of that water in terms of density and dynamic viscosity. And also we are given with the diameter of the pipe, the internal diameter. So this is a horizontal pipe made of stainless steel. At the rate, so this is the volume flow rate, 0.2 feet cube per second. So we would like to get the pressure drop, head loss, and the required pumping requirement input for flow over a 200 feet long section of the pipe. So we listed here the given and also the unknown. So we have here also the schematic diagram for this flow. So first, we need to determine the type of flow before we can use any of the formula because now we have laminar flow or turbulent flow. But we have to verify which is which. So to determine the type of the flow, again, we go back to the Reynolds number. But before that, we get first the average velocity. So using the formula for the average velocity, rearranging the formula since this is circular cross-section. Again, this shortcut formula is only for cross-sectional circular cross-section. But the general formula is this one, the volume flow rate over the cross-sectional area. So this formula is just derived because it is circular. So the average velocity of the flow is 9.17 meter per second. Feet per second. So the Reynolds number can be computed substituting the value from the given and also the average velocity. So we get the Reynolds number to be 126,431.8758. Obviously, this is too far from the from 2,300, so this is a turbulent flow, highly turbulent flow. So, before we proceed to our calculation, we need to get first the roughness of the pipe. So the pipe is mentioned to be stainless steel. So since we are using the feet system, then we will get the roughness here in terms of feet. So the roughness is 0.000007 feet. So we'd use this later on in order to get the different quantities. So the relative roughness can be computed using the roughness that we have in the table, which is this one. And also the diameter of the pipe is also based on the given, that's 0.067167 feet. We can get therefore the relative roughness as 0.000042. And then we can get already the Darcy friction factor F using the Colebrook equation. Take note that you can use actually the Moody chart because you have the Reynolds number and you have the relative roughness. But what you will get in that is actually a very inaccurate result because that is just a chart. But we can get the accurate result by using the Colebrook equation. So this is our Colebrook equation. We just substituted already the value of the relative roughness and also the Reynolds number. So you can see the only unknown here is the friction factor F. So using solve, you can get the Darcy friction factor to be 0.0174. So take note that it doesn't have a unit because that is a non-dimensional quantity. So again, you can use also this table by just intersecting the Reynolds number and this curve here which represents the relative roughness and then project it horizontally to get the Darcy friction factor. So the pressure drop can now be computed using our general formula because this formula is applicable for both laminar and turbulent. So we can substitute the known values. And also here you can see that we have to convert some quantities. You can see that we have a pound mass here. And you know that our pressure is a pound force. Therefore, we need to convert that pound mass into pound force by using the conversion factor. 1 pound force is 32.2 pound mass feet per second squared. So the pressure drop is 11.783 psi. So we just simply convert also the results by dividing it by 144 so that the result would be pound force per inches squared or psi. So the pressure drop in psi is 11.783. So now that we already have the pressure drop, we can get already the head loss. So it's related to the pressure drop by the specific weight. So substituting the value of the density and the gravity, which is also the specific weight, and we convert that into pound force by multiplying it with this conversion factor again, so that we can eliminate pound mass and also the pound force. We can also eliminate the second squared. So you can see that we already have feet squared divided by this feet cube, multiplied by this feet cube divided by this uh, feet here, and then this we have feet. So if you rearrange that, the value would be in feet. So the result would be 27.2 feet. So the head loss is equivalent to 27.2 feet. So the pumping requirement can now be computed using the head loss or the pressure drop or the pressure loss. So substituting the value of the pressure loss and converting it to watts using this conversion factor, we can get the pumping power requirement to be 461 watts. So this is the power that is needed in order to move the fluid from one location to another in this 200 feet long section of the pipe. So this is how you can solve problems involving turbulent flow. So if you're going to examine it, the first step is to really identify whether it is laminar or turbulent. And then once you identify whether it's laminar or turbulent, you can go to the different equations there based on the kind of flow to get the desired quantity. And you can also see that most of the problem will look for the pumping power requirement, because if you can observe that that would be the required when you wanted to move a fluid. So we have here another example. We have heated air at 1 atm and 35 degrees Celsius. The density and the kinematic viscosity is given. Is to be transported in a 150-meter long circular plastic duct as a rate at the rate of 0.35 meter cube per second. If the head loss in the pipe is now to exceed 20 meter, we determine the minimum diameter of the duct. Say for example, you are an engineer and you are designing a ducting system. So the requirement is that the head loss would not exceed 20 meter because you already have the power requirement that you would need. And here you are able to measure the flow rate using a flow meter, and also the length of the pipe by measuring it using a measuring device. Then we can design, or we can specify the minimum diameter of that ducting based on the formula that we already have. So the solution would entail first, identifying whether it is turbulent or laminar. So once you identify it is turbulent, then we can use the formula based on the turbulent. So this is the formula for the diameter if you have a turbulent flow. But take note, this formula is only applicable when the Reynolds number is in this range. So if you look at it in our table, we have a plastic pipe. So therefore our roughness would be equals to 0. So if we go back to our equation, we can actually eliminate the first part of the formula for diameter, thus obtaining this portion already here. If you look at the given, all of those quantities are already given. So we just substitute those values so that we can get the diameter for this ducting. So we can get the diameter to be 0.271 meter. So if you are an engineer, then you would design, for example, that heated air plastic duct to be not less than 0.271 meter. So I hope that you can relate it to practical situations, especially that somehow this is related to your field. Now that we already know how to compute the different quantities and investigate turbulent flow in pipes, we are now ready to move forward to minor losses. The fluid in a typical piping system passes through various fittings, valves, bends, elbows, tees, inlets, exits, enlargements, and contractions, in addition to the pipes. These components interrupt the smooth flow of the fluid, as you can see here in this presentation, and cause additional losses because of the flow separation and mixing they induce. In a typical system with long pipes, these losses are minor compared to the total head loss in the pipes. So the losses that we computed a while ago, which are HL, are considered to be the major losses. So these are called the minor losses now that we have here in this section. Again, these losses are due to fittings, valves, bends, elbows, tees, inlets, exits, enlargements, and contractions. The minor losses are expressed in terms of the loss coefficient, or also known as the resistance coefficient, which is KL, and that can be written based on the HL, or the head loss. No, that's the minor loss. So the minor loss, the additional loss, which is due to the minor loss, which is the losses due to these parts here, if we rearrange this equation, can be written in this form. So we will just need to compute for the loss coefficient or the resistance coefficient. If we know the velocity, then we can get the minor losses. Therefore, the total head loss in general can be computed using the formula head loss total is equals to the head loss major and the head loss minor. The major losses are those because of the length of the pipe, because of the piping itself. The minor losses are due to those parts of the piping systems that I discussed a while ago. The total head loss, if the diameter of the pipe is constant, can be computed using this formula here. So this chart here gives us the loss coefficients KL for various pipes components for turbulent flow. So again, this chart here can only be used if we have turbulent flow, and we can get the value of KL, say for example in the pipe inlet reentrant and the sharp edge portion, the well-rounded, slightly rounded pipe inlet. For the exit, we can also get that using this formula here in terms of if it is reentrant, sharp edge, or rounded. So the alpha here is actually the the energy correction factor. So alpha is equals to 2 for fully developed laminar flow, and alpha is equals to 1 for fully developed turbulent flow. And then we have here another chart for a sudden expansion and contraction based on the velocity in a smaller diameter pipe. So for sudden expansion, we can get the KL based on the diameter at the smaller cross-section, and then a sudden expansion to a bigger diameter. So you can get the KL using that formula. If we have a sudden contraction, we can also get the KL based on the diameter of the larger cross-section and the smaller cross-section. If we have a gradual expansion and contraction, as you can see here in this piping system, wherein the expansion and the contraction is gradual, it is not abrupt, by using by angling, for example, the wall of the pipe, then you can get the value of the KL, which we will need to get the HL or the minor loss based on the angle of this the tilt of this portion of the pipe. So that is equals to theta. The sum of these two angles here with respect to the horizontal is the theta. For bends and branches, which is also very common, you can also get the value of KL. So if it is a flange or threaded, say for example, if you have a miter bend for different kind of veins, we have a threaded elbow, we have a return bend, a T, as you can see here, we have a T line flow and a threaded union. Then you can use this formula here in order to get also the value of KL. We also have, if you have valves, which is very common also, if you have a globe valve, angle valve, ball valve, swing, check valve, gate valve, you can also get the value of KL. As you can see, those charts are very helpful if you wanted to get the value of KL, which will be needed to get the minor loss or the HL. You can also see here where the velocity is located in the portion of the pipe. So let us have an example. So we have here a 6 centimeter diameter horizontal water pipe which expands gradually to a 9 centimeter diameter pipe. The walls of the expansion section are angled 30 degrees from the horizontal. The average velocity and the pressure of water before the expansion section are 7 meters per second and 150 kilopascal respectively. We determine the head loss in the expansion section and the pressure in the larger diameter pipe. So here we have a horizontal water pipe, which you can see here the schematic diagram, that expands gradually into a large diameter pipe. So from 6 cm to 9 cm. The head loss and pressure after the expansion are to be determined. So our assumption in this problem is that the flow is steady and incompressible, of course, so that we can use the formula. The flow sections at 1 and 2 are fully developed and turbulent with a correction factor of 1.06, for example. So we listed here the different knowns, or the given, and also the unknown. So we number the inlet to be 1 and the outlet to be 2, or the larger portion to be 2 and the smaller portion to be 1. So based on our chart, based on gradual expansion and contraction, we can get the value of KL. If you are going to examine, our problem states that the expansion sections are angled 30 degrees from the horizontal. So this represents this angle here with respect to the horizontal. And since we have 2, if we sum that up, then the total theta would be 60 degrees. That's why we have here a theta of 60 degrees. So if the theta is 60 degrees, the value of the friction coefficient KL would be 0.07. So we will use that value in order to get the first unknown, which is the head loss. So using the formula for the head loss in the expansion section, this is actually our general formula. But this time we are looking for the head loss in that expansion. So therefore we are using the value at the expansion, which is the velocity at the expansion, which is V1, which is given 7 meter per second. KL is already found out in the table, in the chart rather, which is 0.07. Substituting the value, we can get the head loss to be 0.175 meter. So say for example, you are an engineer and you are designing a piping system, and you are looking for the power requirement for that fan that will move that fluid into that piping system, then you will add this also in the head loss. So the head loss in the expansion section would be 0.175 meter. So the other unknown is the pressure in the larger diameter pipe. So using the conservation of mass principle, we will first get the velocity at the larger cross-section. We know that the mass flow rate is constant by the conservation of mass principle. Then expressing that in terms of density, the velocity, and the cross-sectional area, rearranging that in terms of the diameter, since this is cross-sectional areas, we can get the velocity at the larger cross-section to be just this ratio of this portion here. So our velocity at the larger cross-section of the pipe would be 3.11 meter per second. So we will use this value later on to get the pressure in the larger diameter pipe. So using the conservation of energy equation in the previous lesson, which is the conservation of energy, we learned that we can actually get the velocities, the pressures, and all those values using this general energy equation. You can see here the P2, which is the unknown in this problem. So this is applicable also for this situation. So noting that Z1 is Z2, since there are no pumps also and turbines involved, the energy expansion for the expansion section can be expressed in terms of Z1. Since we can already eliminate Z1 and Z2 since they are just equal, there are no pumps and there are no turbines, so we can also eliminate this. So this formula will just become like this. Substituting the known values, we just express the pressure 1 in terms of Newton per meter squared from kilopascal. As you can see, we already substituted the value of V2 also here. And then you are already ready to compute the P2. So our pressure in the larger section of the pipe would be 169.127 kilopascal. So as you can see, because of the sudden expansion, there is also an increase in the pressure. So now that we already know the minor losses, I hope that you can already connect it Say for example, you have bends, you have tees, you have those different cross sections, you have those glow valves, for example, in the piping networks. Then you can compute the total minor losses of all those parts of the piping system. So that will be accounted in the piping networks and pump selection. Most piping systems encountered in practice, such as the water system distribution in cities or commercial or residential establishments, involve numerous parallel and series connections, as well as several sources and loads. A piping project may involve the design of a new system or the expansion of the existing system. The engineering objective would be in such project is to design a piping system that will deliver the specified flow rates at a specified pressures reliably at a minimum total cost. Once the layout of the system is prepared, the determination of the pipe diameters and the pressures throughout the system, while remaining within the budget constraints, typically requires solving the system repeatedly until the optimal solution is reached. Computer modeling and analysis of such a system make this tedious task a simple chore. A piping system typically involves several pipes connected to each other in series and or in parallel. As shown here in this figure, we have a series piping system. When the pipes are connected in series, the volume flow rate through the entire system remains constant, regardless of the diameter of the pipes and of the individual pipes in the system. This is natural consequence of the conservation of mass principle for steady incompressible flow. The total head loss in this case is equal to the sum of the head losses in the individual pipes in the system, including the minor loss. The expansion or contraction losses at the connections are considered to belong to the smaller diameter pipes, since the expansion and contraction loss coefficients are defined on the basis of the average velocity in the smaller diameter pipe. For a series, for a parallel connection on the other hand, that branches into parallel pipes and then rejoins at a junction downstream, the total flow rate is just the sum of the flow rates in the individual pipes. The pressure drop or head loss in each individual pipe connected in parallel must be the same, since our pressures at these 2 points are the same for all the individual pipes in order for it to flow, for example. The analysis of piping networks, no matter how complex they are, is therefore based on two simple principles. First, the conservation of mass throughout the system must be satisfied. This means that the total flow into a junction is equal to the total flow out of the junction for all junctions in the system. The flow rate must remain constant in pipes connected in series, regardless of the changes in diameters. On the other hand, for pressure drop and head loss between two junctions, they must be the same for all paths between the two junctions. Therefore, the analysis of piping network is very similar to the analysis of electric circuits, with the flow rate corresponding to the electric current and the pressure corresponding to the electric potential. However, the situation is much more complex here since, unlike the electrical resistance, the flow resistance is a highly nonlinear function. Therefore, the analysis of piping networks requires the simultaneous solution of a system of nonlinear equations. The analysis of such a system is beyond the scope of this introductory subject. In this lesson, we are able to unveil the different concepts related to the pipe flow in conduits or piping system, particularly the difference between laminar and turbulent flow, what the entrance region is, and its significance in the design of piping networks, the laminar flow and turbulent flow, which will help us determine the various quantities that will be needed in the design of pipes, such as the pumping power requirements, the minor losses, which is an addition to the major losses in order to get the total losses, and finally, on designing piping networks and eventually selection of the pumps. See you in our synchronous discussion.